In the name of God, the compassionate, the merciful, Engineering Plasticity, Chapter 4, Constitutive Relations, Part 5. Hardening. Well, hardening comes after what we have discussed in previous parts in this chapter, Constitutive Relations. So far we have discussed the behavior of the material in the elastic range and in the plastic range as far as the first yield or incipient yield. Okay, and we have considered, for instance, perfectly plastic materials like this. Let me just get this laser point. Perfectly plastic materials like this. So when it starts to yield, it continues on the same line like that. There is no increase in stress, and we have only a strain in here. Okay, that's what we have so far discussed, but we haven't discussed this bit. If we have hardening, for instance, if the material behaves like this, it goes on this path from A to B and onwards. What happens then? How do we analyze the material? Which relationship, with which constitutive relations will we use? As you can see here, we have continued past A through point B, and we have unloaded the material. Unloading obviously is elastically. We have introduced the idea of hardening before, and so what happens to the material is that if you unload it here and then start loading it, instead of point A, it goes on to point B, because when you unload it up to here, you got this much plastic deformation, permanent deformation, and therefore when you load it again, it starts from here and goes up to there, which is elastic, and it moves on here. So the yield point increases from A to B. It means that the material hardens, and if we continue on this path again, this phenomena happens and hardening happens. As we go further and further, for more strains we need more stress, while when we were here we didn't need any more to increase any stresses, because at this yield point we get as much as strain we would like. Okay, the material deforms easily, but here the material doesn't deform easily. It is hard to deform, and it becomes harder and harder. Okay, so we are going to discuss this behavior of material after yield point, and assuming the material obeys the hardening laws. Right. Now these ideas can be extended to multi-axial case, where the initial yield surface will be of the form this. The ideas that we discussed, of course, were for uniaxial stresses, because when we extend a uniaxial specimen, that's what happens. This is the stress strain curve for uniaxial test. But we can develop these ideas to the multi-axial loading. Okay, supposing this is our yield function. Okay, F0 sigma ij equal to 0. Why we say F0? Because it's the initial yield surface. Okay, because hardening means that the initial yield surface changes, because for perfectly plastic material the initial yield surface doesn't change, it remains constant. But for hardening, obviously it must change, because as we said here, the yield point is here and then goes there, so increases. so the yield surface must increase, must change. That's why we write down F0 sigma ij as 0, shows the initial position. As I mentioned, in the perfectly plastic case, the yield surface remains unchanged. Yeah, and in the more general case, the yield surface may change size, shape, and position. Okay, for instance, in the Mises case, yield criteria, we had this circular locus, and we had the cylindrical surface, yield surface. Now it says that if hardening happens, obviously the cylinder changes. The cylinder may change in size only, may change in size and position, and even its shape may change. Okay, so this is what we have written here for the yield function for the hardening case. We have sigma ij here like there, but we have a parameter kt or ki, sorry, ki for the hardening. Okay, now as we have shown here, ki represents one or more hardening parameters. These hardening parameters determine the size, shape, and position that the yield surface must change. So we introduce these parameters to show the constitutive relations for the hardening case. Okay, so these parameters change during plastic deformation and determine the evolution of the yield surface. The evolution of the yield surface means that because yield surface evolves from an initial position to another position, it evolves from here to there. They may be scalars or higher order tensors. At first yield, the hardening parameters are 0, and therefore we have F sigma ij 0, the same as this one. So that's why we call this F0. Okay. The description of how the yield surface changes with the plastic deformation is called the hardening rule. In other words, the relationship defining this behavior is the constitutive relations for the hardening case, and we call it hardening rule. Okay. In contrast to strain hardening, we have a strain softening as well. For some materials can soften under the strain. When we strain them, they soften. For example, soils. Okay, in the civil engineers deal with this kind of materials. In this case, the stress strain curve tends down. See, instead of going up, it comes down. So it softens. It means that after this point, which is the maximum stress, for more strain, you need less stress. It means the material is softer and softer as we go ahead, and as we deform it, it becomes softer and softer. Now we are going to introduce different hardening rules. The first one which comes to mind is called isotropic hardening. Isotropic hardening is where the yield surface remains the same shape but expands with increasing stress. As you can see here, the yield function takes the shape of this F0 sigma ij minus k. Okay, the shape of the yield function is specified by the initial function, which is this one, which is this. This is the initial one, and its size changes as the hardening parameter k change. You can see here we have sigma 1, sigma 2, and these are the initial yield surface and the subsequent evolved yield surface. Okay, these two ellipses which we have shown in the 2 dimensions. Okay, so that's the first one. Okay, for the case without hardening and for rigid materials, rigid plastic materials, this remains the same, doesn't change. As you go ahead and increase the strain and deformation. But for isotropic hardening, the same shape which we have shown here, the circle in fact, which is shown here as ellipse because it's 2 dimensions, increases in radius, okay, in size. And as you can see, the increase in size is the same in all over the place, okay. For instance, here, there, the same proportion. This yield surface increases in shape, in size. Now we have shown here the elastic loading. That's the elastic loading up to this point. Here is the start of the yielding, so this initial yield, and then it increases to here, which is the plastic deformation. After this plastic deformation happens, for the case of rigid plastic material, it remains here. It doesn't change, okay. The stress doesn't increase anymore, but the strain increases. But for the strain hardening, the stress also increases. As you can see in this axis, the stress also increases, and it reaches there, which is that point B I showed you in the previous slide. Okay, so that's the plastic deformation and hardening, because sigma has increased. Obviously here is not uniaxial, here is multiaxial. We have shown biaxial here, but we could show it in 3 dimensions as 2 cylinders inside each other, and triaxial stresses. Okay, I will show you later how do we represent the stress and strain in here, for instance. Okay, because we have sigma 1 and sigma 2, how do we represent that point, and how do we strain that point for a strain? So that's after that, if we had elastic loading, we could go back to 0. Then the starting yield surface will be this, not that one. Okay, that will be the starting. That subsequent yield surface will be the starting point. If we unload the material and start loading it again, then it goes up to here is the elastic, and then after that is plastic, and then again another surface will appear. Okay, so that's how it changes. Now, in here for isotropic hardening, obviously I have shown you, I have explained to you isotropic hardening using these circles and ellipses, which are von Mises yield criteria. So I'm going to just to talk a little bit about this von Mises yield criteria. Von Mises was like that, yeah. F0 sigma ij, that's for the initial yield surface, was like that. Sigma 1 minus 2 squared, 2 minus 3 squared, 3 minus 1 squared, minus y over root 2. Sorry, this the square root is over root 2, and is minus y. When you put it equal to 0, you will get this equal to radical 2y, and if you square that one, you get that one equal to 2y squared. So we could show this initial yield surface in this way for Mises, root 3j2 minus y, or root 3 over 2 Sij minus y, where y is the yield stress in uniaxial tension. Remember that, okay? Yield surface in uniaxial tension, not multi-axial tension. Therefore, we could write for the Mises criteria, because in the previous slide I wrote it in a general form, but for the Mises criteria we could write it like that, because in the previous slide I wrote f0 sigma ej minus k. So here I have put root 3j2 minus y instead of f0, because this is for Mises. If you use Tresca or any other criteria, we put for f0 sigma ej the appropriate relationship. So that's the constitutive relation for the or hardening law for the behavior of a Mises material for isotropic hardening. What other kinds of hardening we have? I will introduce to you some other kinds of hardening in a short time, but let's see what we have here. The initial cylinder yield surface in a stress space with radius root 2 over 3y. So that is the initial cylinder shown in the 2 dimensions as ellipse, and why it's shown as ellipse, you know that it's because we cut the cylinder in an oblique plane. If we cut it perpendicular to the hydrostatic line, we see a circular shape, and that's for when we, and that's the pipeline, and that's for when we have all 3 stresses, and we will see 3 stress axes there 120 degree apart from each other. But here we have cut the cylinder up in an oblique direction because we projected it on sigma 1, sigma 2, and we don't have any sigma 3. Okay, so the initial radius is root 2 over 3. We have shown this before, okay, if you refer to previous slides. Now, as this circle develops and evolves into a new shape, the radius increases, okay, y plus k. That's the increase in radius. The details of how the hardening parameter actually changes with plastic deformation have not been yet specified, okay. So that's how it moves, and that's how it evolves, and we get these constitutive relations or hardening rule for isotropic hardening for Mises materials. Now I just want to show you the Drucker-Prager criterion. Drucker-Prager criterion is very similar to Coulomb-Ohm criteria. It is used for stress-sensitive materials. As you can see, the shape is very similar to Coulomb-Ohm, and that's the relationship. So we have this I1 in here, very different from the Mises criteria. We didn't have any I1. In fact, the first invariant is showing the hydrostatic dependent materials, but Mises material, Tresca material are not hydrostatic dependent or hydrostatic independent. So this is again used for soils and powder metallurgy and this kind of things, and we use this alpha parameter here, I1, showing that this is dependent on hydrostatic pressure. As you can see here is shown as we move along this line, the size of the circle increases, showing the yield surface, and it means that yield surface increases in size. Okay, again here depending on what pressure we have, the yield surface, if we have isotropic hardening rule, then the yield surface, yield circle, in fact in here, increases in size. Isotropic hardening and Drucker-Prager, we use the uniaxial tension, and we get I1 equal to y and root J2 equal y over root 3 for uniaxial tension. Note that then K is equal to alpha plus 1 over root 3 y, and this relationship for the isotropic hardening becomes like this. Remember and note that in all these derivations so far, in order to get the constitutive relations, we use the uniaxial tension. Does it matter? It doesn't matter. If you use the uniaxial tension data or use the pure shear test data, torsion and normal force data, any experiments you do, I mean any loading that you apply to a specimen, and you obtain the experimental data, it should fit in the yield function, because yield function is for the material behavior under any loading. It means that if you apply any kind of loading, bending, torsion, combined loading, normal loading, compression, tension, uniaxial, biaxial, triaxial, and the material yields, the same function applies to all of these loadings. So the data from any of these loadings should fit into these functions. That's why we use the uniaxial test, because it's the simplest one, and we get the right answer. I will talk about this uniaxial and multi-axial loading a bit later. Okay, so that's how we get the yield function or the hardening rule. You know, it's more than yield function. In fact, yield function is up to here, but the hardening rule is in this path. Okay. So another kind of hardening rule is called kinematic hardening. As the name implies, isotropic model, the yield strength in tension and compression are initially the same, isotropic. But in fact, it means that the yield surface is symmetric about the stress axis. They remain equal as the yield surface develops with plastic strain. But for kinematic hardening, the name implies, it means that it moves. Kinematic, what moves? The yield surface, you know, as you can see here, the yield, that is the initial yield surface, and that's the subsequent yield surface. The subsequent yield surface in the isotropic hardening also moves, but it moves symmetrically. But here it doesn't move symmetrically. You can see it has an offset. Okay, if the center was here, now the center has moved somewhere else. Okay, but for the isotropic center is the same. Center of both of these circles is the same, but here it's not the same. Okay, so remember, at some points I told you that we will later on talk about Bashinger effect, and we will consider it. So here we are considering it in order to model the Bashinger effect and similar responses where a hardening tension will lead to a softening and a subsequent compression. One can use the kinematic hardening. This is where the yield surface remains the same shape and size, but merely translates in stress space. Okay, so you can see that the shape and size have remained the same, but the position has changed. The position of the center has changed, so it has translated in the stress space. And as you can see, as we go on the strain stress curve, obviously here we have the sigma 1, sigma 2 as the axis, but I mean as we move on the stress strain curve, we first reach the yield point here, and then in the hardening phase we reach here, and the elastic loading comes back elastically, and then when we load again we go into this hysteresis cycle. Now this plastic deformation, as you can see here, there is the stress is like that, okay? But if you compare it to this one, the amount of stress is different, and also you can see here that the negative part of the stress for this yield surface is much smaller than the positive part, okay? While in here the positive and negative are the same, okay? If you move on this axis here, then you move on the same axis, you get the same in compression as in tension. But here you get different in compression and tension, and that's what we want with the Bashinger effect, okay? That's the shape of the yield function now. So F0 sigma ij minus alpha ij gives you this kind of, it's just the translation of the yield surface in the stress space. Okay, so we have this one, and that is the translation. That's the center of this yield surface, and that is the center of this yield surface, and that vector or tensor is shown by alpha ij. Okay, so the hardening parameter here is alpha ij, known as the back stress or shift stress, because it has shifted the yield surface by that amount. Okay, the direction and amount is important. So the yield surface is shifted relative to the stress space axis by alpha ij. We call this kinematic hardening, and it can be used for where we have loadings, so that Bashinger effect is important. We want to take it into account, so we use the kinematic hardening rule. Now this is the last slide in this part, and I would like to show you this figure from the paper I have shown in here. The effect of plasticity theory on predicted residual stress fields in numerical weld analysis, Journal of Computational Material Science. Never mind this weld analysis. These guys have used this figure from plasticity in their paper, and because it's interesting figure, I thought I'd show you this figure here. The last model that I'm talking about here is the mix hardening rule. So we had the isotropic, kinematic, and mix hardening, which is a mix of the isotropic and kinematic hardening. Because isotropic hardening, as you can see here, just the size increases, the position doesn't change. Kinematic hardening, the size does not change, but the position is changed. But in mix hardening, both the size and the position change. Okay, so that's a more general kind of hardening rule. But the interesting thing shown here is a comparison of these three cases with this loading and unloading that we have here. As you can see, that's the elastic part, that's the plastic part. It's shown here as a linear plastic. So that's the point, yield point. As you can see, on all these initial yielding are the same and the same point. Okay, that's the initial yield or incipient yield or the first yield, and then the second yield or the subsequent yield. We have shown it in here, and the isotropic one is on the yield surface here, the subsequent. Okay, and on the kinematic hardening rule is here, and also on the mix hardening rule is here. Okay, and then when we unload it, that's for the uniaxial test. This is uniaxial. Okay, so we have just sigma 2 and epsilon 2. It's a uniaxial test, and we unload it So for different materials, it has a different behavior. For instance, the C is for this material, okay, which shows the Bollinger effect and a very pronounced difference. You see, the yield point in tension, that's the yield point in compression. So that's the elastic unloading. And then D is for the mixed case, which again here you see that yield in compression, yield in tension are very different, and so we get that much. And for the isotropic one, the yield in compression and yield in tension the same, that's the elastic unloading, and we get the same point here as there. Okay, so this is a good figure for understanding the hardening law and comparing them together and see what the difference is. So you can see from here that whatever the material you have, you can use the appropriate hardening rule for it when we go beyond the yield